With the reproducibility workshop. My name is Jimenez. I'm an incubator fellow at Cruz. And for this talk, we're focusing on reproducibility, and we have two great talks. The first one is by Romain Jacob, and the second one is by Tanu, Malik. So Romain Jacob is a postdoctoral researcher in computer engineering at ETH at the Computer Engineering Networks Laboratory in ETH Zurich, and his current research interests are focused on computer networks, communication protocols, scheduling theory, and statistics applied to experimental design. His dissertation is entitled Leveraging Synchronous Transmissions for the Design of Real-Time Wireless Cyber Physical Systems. He obtained a Master of Science in Engineering of Complex Systems and a Master's for Faculty Training for Higher Education, both from École Normale Supérieure de Cachan in Paris. And in 2014, spent a year in UC Berkeley as a visiting scholar under the supervision of Professor Carl Hedrick. Romain is an open science enthusiast, and he tries to advocate for open science whenever he can. And he's also involved in science communication projects. So the title of his talk is IoTBench, Reproducibility Challenges in Wireless Networking Research. Without further ado, let's listen to the talk.
Hello everyone, my name is Romain. It's my pleasure to be here with you today, although virtually, to tell you a few bits and pieces about IoTBench, which is an initiative I've been involved for the benchmarking of wireless communication protocols. And in particular, I would like to stress some of the particular reproducibility challenges we have been faced across the spectrum of this work. So this is me as a cheap attempt to make this presentation a bit more human feeling. So I would like to start off by asking you a very simple question. Think whether or not you have ever performed an experimental evaluation of whatever you might be working on. Software system, a hardware design, a protocol evaluation, whatever it is. Given the audience that I expect to be from the Cross Symposium, I would say the answer is most likely yes. But then the follow-up question is, how confident are you that if you were to run again the same evaluation, you will find the same results? It's not so easy, isn't it? And you should not feel too bad about this. You're actually not alone in this. Some years ago, researchers were surveyed and asked whether they think there is something of a reproducibility crisis in their field, and a very large majority of them said that there was indeed a problem with reproducibility irrespectively of their field. So why is that? Why is reproducibility so hard? My main takeaway for you today is that reproducibility is intrinsically linked to being able to have quantifiable confidence in some performance results. In particular, it is not possible to have reproducibility without quantifiable confidence. In my PhD studies, which I completed last year, I was working in wireless communication protocols. One of the problems we face regarding to reproducibility in this context is external interference. This is the reason why, as you can see on this picture, we sometimes do our experiments within an anechoic chamber so that we can shield ourselves from external noise, and thereby trying to enhance the reproducibility of our setup. If we don't do this, well, actually, we have to face the real life of the RF noise, the radio frequency noise. You can see here a short video I made some time ago of a power analysis. The takeaway is that things move very quickly over the frequency space or the time axis. It's beyond our control. It's a huge mess. And this is really problematic because when you're faced with this very common question is, how does your whatever compare with the state of the art? What you want to be able to do is to run your system against some sort of benchmark. And so we came to the same conclusion. It's okay, we need a benchmark for our protocol we use in IoT devices. And because we're very inventive, we call that IoTBench. So what is the vision behind IoTBench? What is it we are trying to achieve here? So the idea is as follows. Let's say you've been designing your cutting-edge communication protocol and you want to see how well it performs and by how much it beats the other approaches. At least that's what you hope for. Our idea is that you would send your binary file containing your code to IoTBench. That will take care of automatically run your binary against some benchmarking scenarios. And then you will receive those results back so that you can put in your plot for your next paper. We will also store your binary so that we can repeat automatically evaluating your protocol over time. We will store this evaluation results of your and other protocols so that we can eventually and finally compare different protocols against each other and have some sort of reproducible evaluations. So here, the comparison of the results is really what we are interested in. That's really the end game as far as the benchmarking initiative is concerned. There are, of course, quite a handful of challenges there. The first issue we face is that typically researchers use a very wide range of settings for their experiments. Here you see only 3 dimensions, which are the time interval between packets, the number of devices we use to test our protocols, and the number of runs that each paper reports. And you can see that the data is all over the place. Like no 2 people are doing things in the same way. So that makes it very difficult to eventually compare their results. Furthermore, the papers themselves are not meant to be reproducible artifacts. Like they don't provide often enough. They don't provide enough information in order to be able to rerun the experimental campaign should you wish to do that. And finally, it's often the case that you do not have the reference results. You have the result from the paper, but you cannot rerun the code of the protocol because it might just not be available or the experimental setup is not available anymore. So how do we want to address this? There's a handful of things one can do. And in this talk today, the 2 aspects I would like to focus on relates to the methodology and in particular how to design the experiment and how to compare results with one another. So again, main takeaway of my talk, we cannot have reproducibility without quantifiable confidence. So essentially we have shifted the question of reproducibility towards how do we get quantifiable confidence? To do this, we have, I would like to propose a 3-step approach. First and foremost, we need to understand the type of variability we are faced with. Once we know the source of variability, we can use the right statistical method to handle them. And then finally, we can put all that together so that we can provide confident claims. So let's start off with the variability. What does reproducibility mean? Right? What we are saying informally is that an experiment is reproducible if you can obtain the same result under the same conditions. As I mentioned, with RF environment, it's a bit difficult to obtain the same condition, almost essentially impossible. So we know we expect performance variability. We will never obtain the exact same results. And this problem is not peculiar to wireless communication. It happens also in tons of other, actually most of other experimental research. So what type of variability, right? We know we expect some, but how does it look like? So let's take a time axis of experiment and see what we are essentially doing. Let's say we measure some quantity x, which can be anything you're interested in over time, and you observe some variations like this. What you would do typically at the end of your run is that you will aggregate this information by computing some kind of metric, for example, the mean. But of course, you're not going to do this only once. You will do that a handful of times, which we call the series. And for every run, you will obtain one value of your metric. So now you need to summarize data one step further. And this is often done by using what is known as KPI. That stands for Key Performance Indicator, where you would compute against some kind of aggregate of your metric values. Could be the median, could be, again, the mean, doesn't really matter. But then it doesn't actually stop there. Like if you take this series of run and you repeat it 1 month from now, or even 1 year from now, chances are very good that you will not obtain the exact same KPI value. So the value of X varies. This is why we compute the metric, but the metric can vary, and the KPI computed based on the metrics will also vary over a longer period of times. And those are 3 different scales of variability that our experimental design has to handle with. So how do we do this, right? The goal is that each of those values should be robust estimates. What does that mean? It means that it should be able to tell me how many runs I should have in a series. And we have actually other questions that are related to this, that are how long a run should be, how long the time span of a series should be, and how many series I should perform. And the overall objective of the experimental methodology is to find a rational answer to these questions, right? Obviously, if we take how many runs, 1 run is not enough, 1,000,000 runs is most probably too much. So what is the right trade-off in between? And what our goal is really to try to quantify this trade-off between the amount of effort we put in our experiments with the resulting confidence we're going to have in the numerical values. And to do this, we need to resort to the appropriate statistics to handle the different variability that we may face. So I will focus in the rest of this talk on the second question: how many runs should we have in a series? What does that mean? Why are we trying to answer this? Or actually, more precisely, what are we doing when we try to answer this? What we're saying is that the KPI, the value we compute based on the series of runs, should keep reasonably the same values if a bit more or a bit less of the runs were performed. So effectively what we are doing is that we based on a few runs, because we cannot run infinitely many, we are trying to estimate the KPI value, let's say the median for the sake of argument, of the underlying distribution of the metrics. So this distribution we don't know. We are trying to estimate it based on the samples, and more precisely, we're interested in 1 statistics from that distribution. This is the underlying process that we are trying to fulfill here. How to do this properly? One way of doing this is to use what is known as confidence interval, which informally stands for a numerical interval in which the true value of something lies with a certain probability, which is known as the confidence level. So on the right side, you can see an example. If I say that AB is a 95% confidence interval for the median of some quantity X, it means that the probability that the true median of X, which I don't know, is within A and B with a probability larger or equal to 95%. Now, which KPI should we use? Often enough, in the literature, you will see used the mean and the standard deviation as information for the central tendency and the spread of our distributions. And this is often enough because used as we have this picture in mind. The problem is that this works only if you know that the underlying distribution of your matrix data is normal. And I'm sorry to tell you that, but in 99.9999% of the cases, this will not hold true. In computer science, most of the experimental data we have is not normally distributed. So we have to resort to what is known as non-parametric statistics. That is, methods that do not make any assumption on the nature of the underlying distribution. Consequently, one should not use mean and standard deviation because somehow they don't really help us arguing about the overall distribution. Instead, what we recommend in our work has been to use percentiles as KPI. The reason we recommend this is that it actually exists rather a simple non-parametric method to compute confidence interval for percentiles. Here is an intuition on how this works. Let's say we are interested in estimating the location of the median of this quantity X, and we take 1 sample, just 1. What is the probability that the median is above this sample or is below that sample? By definition of the median, it's going to be 1/2 on each side. Now, say we take a second sample independently of the first one. then the probability multiplies, and it is the median is below both samples with probably 1/2 times 1/2 equal 1/4. Same on if it's above both, and in the middle it's going to be one of each, so probability 1/2 again. We can repeat this process with 3 samples, 4 samples, and as many samples as you want. And essentially, you can show that the probability of any percentile P of P to lie between 2 successive samples follow a well-known distribution, which happens to be the binomial distribution in this case. And you can play a bit with the math so that you use this to compute confidence interval for any percentile you're interested in. The nice thing about this, this method is that you can actually revert it to get the minimal number of samples n you need to make any estimation at any confidence level. For example, if I stick with a 95% confidence interval, if I'm interested in estimating the median, I need only 6 samples, which is rather okay. Now, if I want the quartile, it increases to 11. If I want the 95th percentile or the first percentile, this increases already to 300. And then if some of you are familiar with industry standards, we often talk about, or you hear about those 5.9 level of reliability. So if we plug in the math, it means that we need about 300,000 samples in order to get a 95% confidence interval for this percentile. So yeah, pretty much we can forget about it. More visually, here's how this looks like when you start adding more and more samples to your set. So once you do 1, 2, 3, 4, 5 samples, you still don't have enough. Then you reach 6 samples, which, as we saw just before, is the minimal number of samples you need to get 95% confidence interval. So in other words, you know that between the minimal and the maximal of your samples, the probability of the true median to lay in that interval is larger than 95%. And then as we add more and more samples, we're going to start being able to exclude extremal values from our estimate interval. And this will go on and on and on, and eventually, as intuitively expected, the more samples you have, the narrower your confidence interval will tend to get. All right, so this is an example of using the proper statistics for the intended purpose. Now, finally, we need to glue all those things together. How does that help me? How do I use this knowledge to help me design and analyze the data that are coming out of my experiment so that I can eventually reach reproducibility or improve on my reproducibility at least? For that, we work on a framework which we ended up calling TriScale to precisely help you doing this. So we reuse the 3 time scales that we have seen earlier with runs, series, and sequels. For each of those, we have 2 different pipelines, one for design, one for the analysis. In the design pipeline, you find the questions we had before. And for example, for the series, how many runs do we need in order to reach the confidence we're interested in? And what we put in this pipeline, in this design pipeline, are the evaluation objectives. What parameters are we trying to estimate? What metrics, which KPI, which confidence level do we want to achieve? You run through the pipeline and then you get essentially the description of how much effort you should put into your experiments, how many times you should repeat your experiments, essentially. Once you have this, you can perform your data collection, which is beyond the scope of the framework. And once you have the data, you can pipe it through the analysis pipeline, which will take care of running the appropriate statistics to compute the metrics, the KPI, and what we call the variability scores in the end. And we'll give you this performance report, which is associated with quantifiable confidence level, and therefore significantly raises the bar on the reproducibility of those results. Practically speaking, TriScale is a Python module that you can use. It contains, as I mentioned, all the implementation of all the statistical methods you need, as well as some visualization to help you in the process and understand what's going on with your data. If you're interested for more detail, it's actually much more, there are many more things that I just have the chance to tell you in a few minutes. I invite you to check the paper. The code is already openly available. It is still anonymous as this work is under submission. There is even a live demo on GitHub, so you can just click a link and go and have a look at the functions and how they work within Jupyter Notebook without having to install anything. So really, to summarize, the goal of this entire process is to move away from making bare performance claims, simple claims without really foundations, to scientific claims where we have grounds to say, those are the results I have, and this is the level of confidence I expect should you try to reproduce my experiments. So again, reproducibility is intrinsically linked to quantifiable confidence. And more precisely, there is no chance of getting reproducibility if you cannot quantify the confidence in your results. That's my main message for you today. And so then the question is, how do we get to this quantifiable confidence? Argue that you need to understand which source of variability you have in your system, use the appropriate statistical method in order to compensate for this variability, and finally, put that together to make robust claims. This is a work that I haven't done on my own, so I would like to acknowledge some of my collaborators here. And if you should be more interested, you will already find the slides of this presentation online, as well as the TriScale paper, as I mentioned.
Thank you very much, Romain, for that talk. That was really great. Any questions? Let me check on the document.
So maybe if you allow, while we wait for a question, I would like to quickly ask the participant a simple question.
Sure.
Do you mind? So let me try to quickly share my screen. Yep. So I would like to ask you a simple question. It's an online poll that you should see now. I would like to know how many of you have heard about the replication crisis that I mentioned in my introduction before today. So to do this, you can just go to www.menti.com. There will be asked for a code, and you can enter 50, 52, 22, and we'll start seeing the answers popping in there. Just some discussion we had in our local kind of journal club sometimes earlier this week, and I was curious to have some data from your guys' side. I can let that running while we wait for the first questions to pop up.
Yeah, I have a quick question regarding from the practical point of view.
Mm-hmm.
If you have any sort of systematic approach to experimentation for running experiments, right? You
Mm-hmm.
have, since you have this more rigid approach in general, I'm not talking just about this framework, then you have this loop, right? And sometimes experimenters might feel that's not quick enough, or that sometimes you need to kind of like work around issues of that are ad hoc to what you're doing. Do you see something like that? First of all, is the question clear? Like,
I'm not entirely sure. So you're referring to the TriScale framework for designing your experiment, right?
Like at the beginning, you had this diagram where you have a researcher and then you submit.
Yeah, the vision of the benchmarking. Yes.
Yes. So you have that loop, right?
Mm-hmm.
And depending on how long that loop takes.
Yes. Okay. So let me comment on that. So that will be obviously very context specific. In the context of IoTBench, so we are talking about benchmarking wireless communication protocols. Usually what that means, so we run all this on public testbeds, so you can access through a web interface, you can upload your binary files, and then the test is being programmed and runs automatically. This already exists. And the tests are not meant to be extremely long. So like a long test would be something like an hour, because in the community I'm coming from, or at least I was working on at that point, we're studying low power communication protocols, and the point was precisely to try to assess, of course, the reliability, but also the energy consumption that you would have over a longer period of time. But you cannot just let your network running for 2 years. Like, other people need the test bed as well for their experiments. So typically we would do like, yeah, something of like an hour would be a long test. And myself, and as you can see from, you can guess from the ideas from TriScale, you actually benefit from more runs, so more repetitions, but that can be shorter. And then you can get you can make more interesting statements based on the statistics with fewer, more short runs than fewer long ones. So I would even argue that this feedback loop, you can make shorter and shorter because the runs don't necessarily need to be super long. That obviously will depend on what you're working on. Like if you're working on some system that runs, I don't know, if your scenario is a month, then it's a month and you need to run for a month, and there's nothing one can do to shorten that.
Cool, thanks. Any other question?
So there's one question on the minutes from Lisa.
Yeah, I can just repeat it in person. That might be a little bit easier. So yeah, you mentioned that you spent a good amount of time explaining confidence intervals and percentiles. Thank you for the very clear explanation. I think it was quite good. But I know that, or at least from practice, a lot of confidence interval type of reporting tends to be misconstrued in a good amount of research. So like instead of saying, oh, like 95%, or rather 95% of these intervals have the average in it, and this is one of the intervals. A lot of people say, oh, there's a 95% chance that the mean is in this confidence interval. And so to kind of avoid this inaccurate interpretation, a lot of recent research, at least in say like education or biology or social science, has instead focused on using bootstrapped measures. So for example, that means that you report the mean, but you also report bootstrap standard error, which is you take the original data distribution that you have and report 10,000 times, just kind of try to measure the standard error. So does your platform also enable that sort of bootstrapping, or is there any chance that it will be part?
So that's a very good point. So bootstrapping, as you briefly explained, is a different method that can be used that based on resampling. That is another approach that allows to build confidence interval that are purely experimental, meaning that we empirically observe that those confidence interval work or somehow are representative, but we don't have like a mathematical proof that kind of like justify why this interval works because it's based on resampling. I mean, it's not the only reason, but anyhow, back to your question. Not strictly speaking. So in TriScale, we made a choice on which method we wanted to use, and we used this Thompson method that I've illustrated for the computation of KPIs. Actually, in some other work that are not yet in this paper, we have compared on test cases the accuracy, or let's say the convertiveness of the different approaches. So let's say that if you do sample from a normal distribution just for the sake of argument, then you can compare the confidence interval based on the parametric method, then the one based on the Thompson approach, which obviously will be less precise because you have less assumptions that you made, and the one from bootstrapping. And in almost all cases, the bootstrapping confidence interval tends to be the most pessimistic one, so the larger one. It would obviously not be always the case, but that's what we have observed. So we are not pushing too much for this because it so happens that at least in the data we've observed and the experiments we've done, it is not it's not the best in terms of quality confidence interval one can get. Although there are some cases where bootstrapping is the only thing you can do, and you don't have any other choice. Like typically, if you cannot reasonably make assumption of independence between your sample, I think bootstrapping is the only thing I know that you can use that still kind of provides something reasonable that at least you can work with.
Thank you.
All right. Let me check. I don't see any more questions.
I don't see either.
So do you want to, were you planning on going back to your poll?
Yeah, I've got 9 answers, 4 yes and 5 no. And I was quite curious. So for those of you that might be curious, I attended a presentation from a public survey, so general public, and where general citizens in Germany were asked whether they've heard about the replication crisis, and they found about 25% of people have heard of that. And we had a bit of a debate whether this was a high number or a low number. And I was more laying on the side that 25% on the general population in Germany, that sounds like quite a lot. And I would bet that there's a strong sample bias in those results. And so we were arguing that it would be interesting to take like academic crowd where you would expect people to know more and see how that would compare. So it was just like a quick experiment, and we see roughly
And
half.
what were your percentages? You said you got 9 votes, and how many people?
9, 4, and 5. 4 yes, 5 no.
Okay. Yeah. Cool. Thanks. Well,
Right.
thank you very much, Romain. And
Thank you very much for having me.
Yeah, thanks. Appreciate it. It must be late for you.
It's okay. It's still 8-ish.
Okay. Cool. Thank you. Thank you very much. Okay, so our next speaker is Tanu Malik. She's gonna be talking about reproducibility in the context of containers and container technology. Tanu Malik is an assistant professor in the School of Computing, and she directs the Data Systems and Optimization Lab. Her research interests span topics in database systems, data provenance, distributed system, and cyber infrastructure for scientific data management. She received the 2019 NSF Career Award for her work on computational reproducibility, and she is also a current 2019 fellow for the Better Scientific Software Fellowship. And she has actively collaborated with scientists across several institutions, and her research is funded by NSF, Department of Energy, Sloan Foundation, and the Bloomberg Foundation. Okay, let's hear her talk.
Good morning, everyone, and thanks, Ivo, for inviting me to give a talk on reducing technical debt with reproducible containers. This is work done under a Better Scientific Software Fellowship. A little bit about myself. I'm an assistant professor at the School of Computing at DePaul University, and my primary research interest is in data provenance. And I'm exploring how provenance can be useful for computational reproducibility. In general, I'm interested in building data management systems for scientific data. And today I'll be presenting one of those systems, SciUnit, for computational reproducibility. But before I present SciUnit, let us ask the question, what is technical debt? So we all are familiar with some fiscal debt on commodities, such as a house, a car, or the credit card. Now, a fiscal debt is a weight or a burden that we choose to carry to meet an objective. Often taking on that debt to buy the dream house not only gets us the house faster, it is cheaper than the alternative of continuing to rent. Technical debt, introduced by Ward Cunningham in 1992, is no different. To be clear, in science and academia, the commodity is often the paper, and since research is mostly computational, it increasingly includes the software accompanying the paper. So in technical debt, over time, the paper review process, based on the various deadlines, submission, rebuttal, camera ready deadline, helps us improve the quality of the paper. but there are no similar deadlines for the software that accompanies the paper. So it is our intention to write good scientific software, but in the end, we end up writing poor scientific software, thus accumulating technical debt over the period of time. Now, software engineers have tried to qualify this technical debt. They've tried to determine the dimensions of this technical debt, such as poor quality code, poor design, not knowing the environment. So you are writing a scientific software, but the software's environment has not been completely known. There is lack of documentation, or they are missing tests in the software. Researchers are, the software engineering researchers have also strongly suggested that technical debt must be paid over time. But what if we don't? Now, if we contrast it with the fiscal debt situation, there are consequences of mismanaged debt. If the debt is not repaid, then the commodity gets confiscated. So should a paper be retracted if technical debt on its software is not paid? Well, increasingly, this is becoming true. In conference publications, the paper is being termed irreproducible by conferences. So how can we pay technical debt with minimal investment of time? And that is the topic of sort of my today's talk, where I'm proposing that we need something like a notion of a reproducible container. And the idea is that it's a container system, so it gets your dependencies. Containers have become very popular in DevOps, but we need to make them useful for reproducible science so that we can pay technical debt with as little human intervention as possible. Now, in today's talk, I'm going to lay the vision of such a container, and I'm sort of going to focus on two kinds of debt: the environment debt and the documentation debt. Now, before I begin my discussion about reproducible containers, for a moment, let's talk about containers such as Docker and Singularity. Now, as most of you might be knowing, that containers provide secure resource isolation. So we have resources such as CPU, memory, file system, network, and as you can see, these green, yellow, and blue lines, the resource gets isolated into a specific quantity. So you can say, well, 200% of the CPU, 20% of the CPU is allocated to a given application, another 40% is allocated to another, and another 50%. So you can allocate your resource based on C groups, and then all the programs for that particular application remain constrained within that isolated environment. But containers do not help us pay technical debt. They do not address the issues of technical debt. In particular, the environment debt must be paid manually. So if you look at our containers like Docker and Singularity, they require programmatic description of dependencies. One has to program a Docker file to tell what must be contained within the container. And within that, we also have, the user also has to specify the specific library versions that the application is using. Not only that, once the container is created, there is no guarantee that that container only contains files that are necessary for that application. The application may consist of anything irrelevant as well. And none of these containers are ever documented. Like the way GitHub repositories are documented. You'll have a README or something, but you don't see such kind of READMEs for Docker images, for instance. So the reproducible containers are aiming to address some of these issues that are there in regular containers, trying to introduce methods within the specific container so that there is less and less programmatic need. There's less and less need for documentation. So I'm going to introduce the first topic for this, which is the programmatic encapsulation. And the project that we have for programmatic encapsulation is called the SciUnit. What SciUnit basically does is create what we say as the reusable research object. So the key idea in the SciUnit is to observe an application execution and use the trace to encapsulate the application data dependencies. Now, these application data dependencies could be binaries, could be data and system dependencies, could be environment configuration, and create a provenance graph, which can be used for describing the application itself. So the fundamental thing is that, well, when you are creating a container, you're describing the content, the application in some specific terms, often in terms of packages or repositories that must be included within the container. So here in SciUnit, the key idea is, well, why don't we just observe the application, observe its execution, and if the application must be using all the files that it needs, and if we can just containerize them, just at that time determine what the dependencies are and put them in a container, well, that's where our container would be automatically ready. So in SciUnit, the first phase is encapsulation. The idea is, again, as I said, to observe the application through application virtualization mechanisms, and we use ptrace, LDD, looking at all the dependencies that an application has, and copy those dependencies into a self-contained a directory where the directory hierarchy is maintained exactly as it would have been in the host system of a user. For instance, Alice over here. So Alice has a host system over here, and that exact host system is created within a directory on Alice's computer. So you get an encapsulation of the application, and then this encapsulation can be moved on to Bob's computer, for instance, and a simple replay of that application could be is done by redirecting the calls, again observing the calls that are being made to the target file system and the target OS of Bob's computer. And instead of making those calls, such as a change directory over here or open over here, the calls are redirected into that encapsulation system. So this can be done by mechanisms such as change root. You can also do it like that without needing containerization as such. Little bit details more that while we are observing, we also capture its provenance graph, and we create this directory structure. So over here, Alice is using the file system, and the file system is exactly created over here. But we create a container as such, in the sense that when the application is rerun, it's run in an isolated manner. That means it's run in its own namespace. Before we start the application, we isolate the application, its CPU, we isolate the network namespace, and so it's run. The new application is run kind of the container style. So it's not exactly a Docker container. We don't use Docker, but by introducing isolation right when the application starts, the application is isolated. Now, once the application is isolated, one may say, well, the entire application is isolated. Why do we need to redirect the calls back to, why do we need a redirection again? Because the entire application is isolated. Well, there are further motivations for reproducibility that we need to also verify that exactly same files are being accessed, and do a provenance graph matching of what the original execution was, and the new execution is matching with the original execution. And if it is not, then say with certain guarantees that it is not matching. So I'm not going to be going into the details for how the provenance graph matching happens. We're talking about technical debt, so I'll continue to focus. And there are other papers that I have which talk about the provenance graph matching problem while redirecting. So here is a sample interaction of SciUnit. We can create a SciUnit over here, for instance, in FIE. So FIE is just a name of a SciUnit. It works very much like a Git repository. And you run your application, for instance, a shell script, which is reading an input data file. It's running the application. Well, just by running that application, the SciUnit is created. So you can list that SciUnit, you can show the details about that SciUnit, you can push it on the cloud, you can copy it to another machine, you'll get an identifier, and then the other user can just use this identifier to download the SciUnit and repeat it. So now this execution is being repeated within the container by isolating that computation without it being run just in the native target system. And there are other features that we have added, such that you can change the process, or you can change the data file with which you are running a given execution, just to introduce more levels of repeatability, such as changing data files. Now, this whole thing is programming language independent. We have tested on multiple programming languages like Python, C++, Fortran, Julia, so all these, and we've sort of tested the SciUnits that are created again into on Exceed and on Cloud Lab. So this helps us, as you can see, just this observation helps us take care of the environment debt. And now I'd like to sort of, given the time I have, present how we take care of the documentation debt. And the system over here is the DepGen. It provides dependency and data enumeration. So let me introduce a little example over here. So here is, a scientific code which is associated with a paper, and it's known as the SUMA model. It's a computational model in hydrology. And as you can see, this is the GitHub repository for it. And here I have tried to zoom in on the documentation. Now it says how to run local PySUMA locally. Well, you need to have all these dependencies for it. So our question is that, can we actually generate this automatically? We already have the SciUnit, and somebody actually had PySUMA running. So can we actually generate this README file automatically for them, because we have observed? So if you remember, I said that while we are running the application, we are already observing how the application is accessing various kinds of files through a provenance log. So these logs are created by tracing the system calls to the file system, and they are of the form that, well, you're reading this file, you're writing this file, and so on. So these can be helpful for us to determine that, what particular packages have been used. The only problem is that if you look at these logs, they are in terms of files, right? Whereas if we are documenting over here, they are in terms of packages. So how can we turn the information in these files, which is exactly at the file level, to something at the package level? So the container log consists of paths to individual files. We need to identify, well, what are these? Are these input files? Are these output files? Are these process files, right? Any process that might be running also is a file. Or is it a system dependency? And if it's a system dependency, what particular package it belongs to? So that is essentially the automatic container documentation problem, which is, can we identify packages from container logs? That is, establish the mapping between the specification of a file name with an established package name. Now, it turns out that this is not a very easy problem to solve. Different programming languages have different file paths for packages, and they have different mechanisms also of asking the files. What will apply for Java does not apply for Python. But what we have been able to find are consistent patterns that can be identified across languages. So that is essentially the function of DepGen. What it does is it looks at the container log. So once you have created a SCI unit, you'll get a log along with that. The DepGen is the circle over here. It identifies what are the inputs, outputs, processes, and dependencies. And it creates documentation. And from that documentation, we are hoping that we can create a Docker file, which we have done for the sample cases that we have experimented with. So determining inputs, outputs, and processes are easy. We have a graph. Anything which has no ingoing edges is an input, no outgoing edges is output. Processes are with edge-to-edge node. There is it's a direct fork relationship or an exact relationship which we can monitor. The issue with these log files are filtering noise. There is a lot of activity which is happening within interpreters and compilers where they are simply checking whether a package is existing or not. So we need to remove those files, because a check does not mean that the package was actually used, was actually read, or its files were actually read by the package. So even if we remove this noise, we still cannot say that, well, this file is from a specific package, because the file names do not typically correspond to a package name. So a package name may not even appear in a given file name. So there we use the standard querying mechanisms, which luckily come along with multiple package repositories. So for Python, you can use pip search, and for R, you can use the query CRAN on the website to determine, well, a given file belongs to which particular package. Now, this is a very slow process. We need we realized that actually generating a documentation can be roughly a 10 to 15 minute long job. So we do not want that, and so we build an internal database so that we can continuously, if we have queried for a given file, we don't query it again. So here is a result for the previous experiment that I showed you. This is for the PySumma. So as you can see, there are lots of packages that DepGen reports. DepGen reports, well, any Python built-in packages. DepGen reports sub-packages that might be packages that are already present in the packages that a user is going to install. So here are the packages that were listed in that GitHub repository that I mentioned. And we only identified these packages over here. In fact, Seaborn and Jupyter themes were internal packages to the identified packages. So nobody had to explicitly install Seaborn or the Jupyter themes. So we repeated this experiment on a large number of scientific use cases. We looked at about 100 of these artifacts, mostly on GitHub and Zenodo. As it turned out, not many of them could be SCI unitized. Like, we couldn't observe the application execution. We couldn't get them to run. Some of them are missing something, which is actually in the source code, or the source code actually fails to run. And if that is there, obviously those repositories are not useful. That's one indication that one needs something like a reusable research object, so that when you download them, there's a guarantee that they can be run. Only 20 of them we could run, and we could contain them in SciUnit. Where the dependencies were not listed, we ran them in our own virtual machine, and we installed our own packages. We use two metrics, precision and recall. In recall, we are looking at how many packages the user listed on the documentation and how many did we identify. And in precision, we are looking at the total identified packages, like, you know, how many we identified quite a few, and how many of them were actually listed by the user. How many identified packages were mentioned in the documentation. So we sort of see what is the quality of DepGen. So here is the result from Zenodo research objects. These are all scientific use cases. You know, in this paper, we have the GitHub links, the Zenodo links to all of these projects. As you can see, the precision is not one. Not all the user listed packages, the identified packages are less. So the user is often overquoting the amount of packages. Those many packages do not need to be there because if you look at the identified packages, most of those packages have to be, you know, they're sub packages essentially. So if you look at the precision, how many packages we mentioned and how many we could identify, the precision is less than 1. So we are identifying a lot of packages, but you know, some of them are the identified packages. Over here, we are seeing that the recall is 1 over here for these examples, and the reason for them being 1 is that actually they did not have any documentation. So instead of saying that the user listed packages is 0, we have mentioned that it's 1 because we could actually install them. We could get them to run. So it was really useful for half of them to actually automatically generate the documentation for them. So here's the summary that the technical debt is inevitable while developing scientific software. I really encourage you to go back to the Parker paper. It's too short a time to present the whole thing and the you know, some very interesting results that we have. So I'd like to conclude over here. The technical debt is inevitable while developing scientific software. Unpaid technical debt affects reproducibility of scientific claims, and the technical debt of encapsulating dependencies and the documentation of dependencies is something that we are showing is tractable. There are two methods that we are using, SciUnit and DepGen, and I encourage you to go to this website, sciunit.run, for more results. Well, thank you, everyone. This is acknowledged to the Exascale Computing Project, PSSW Fellowship, and NSF for these funds. So thank you, everyone. These are my collaborators and the student.
Thank you very much, Tanu. And Tanu is available for questions. Is there any question? I have a quick question. So the alternative of trying to reconstruct all these environments, right, it's to ask upfront a researcher to declare dependencies, right? Like in the case of Python, like a requirements.txt file. Do you feel that's too much to ask, given that you're trying to reconstruct? Or in practice, what do you see people struggle with this approach of saying, okay, declare what you use in terms of, I don't know, NumPy, pandas, whatever?
So it's definitely this declaration part is essentially it's a function of the skill level, right? Just to give you an analogy, and this is coming from way back when I was a graduate student, that I was working with astronomers, and my co-advisor, Alex Zale, would say, well, we need to create tools so that astronomers can learn how to write SQL queries. And what is there to learn in that? I mean, it's as simple a language in that, and I couldn't like understand, but which I now do, that's not what their main job is. Is their main job to enumerate dependencies for the application, write a Docker file? That's not the job for, or this is not what the main focus for, let's say the scientists is, or domain scientists who are working in geoscience or in biology and all that. So it's not difficult. Is it very challenging? Well, maybe not, but it's not what, there is a learning curve, I would say, and that is why these IDEs or things which automatically do us automatically enumerate for us helps, especially when things are time constrained. When people have to submit, let's say, artifact evaluation forms, and those forms are very big, as we are seeing in at least in supercomputing. If people have to do it in very restricted time, tools help.
Yeah. Okay. Thanks. Any other question? I have a follow-up if no one else. How do you deal with data? Like you talked about the software. What's your vision on how we should deal with data in the context of containers? Oh, you're muted.
I'm muted. Well, thanks for that question. Yes, that's an important thing. So there are two things that we do for data. In SciUnit, the current mechanism is binary. You either include the data or you don't include the data, and that's just a configuration option. But more recently, we have started looking into that. Can there be an option for including data, just the data that the application is using? So oftentimes it happens that the application is reading in a large file, but is using very few bytes from that large file. So can we just include those few bytes or some extra around that, which we think potentially an application can use into the container? So there is one line of research which I have not included in the current presentation. It was part of the PDEX workshop that Ivo had organized. It's in the area of, the system is MIDAS. So if you Google that in PDEX, you'll get it. The idea is to use, sort of look at the compiler, sort of the control flow, and do a partial evaluation of the program to understand what particular data segments are being used by the application, and then just include those in the container. So yeah, that's very important, a very important question.
Thank you. Okay, well, I think if there are no more questions, thank you very much, Tanu.
Thanks,
for your time and your talk. Thank you, appreciate it. And next is me. And I'll ask for your, I have to apologize, but I didn't record in advance. But I hope there's no any issues trying to show my slides. This is for people that I see many people new in the audience. This is, and if you were yesterday at the IAB, this is gonna be kind of like a repeat of what I talked about yesterday. But for those that are not aware of Popper and what we're doing in the incubator project, this is an introduction, and also I, at the end, would like to try to pitch an idea for Popper Cloud, and I am very interested in what is your feedback on that idea and whether that's something you see would make sense, would be valuable for, in general, for people doing experimentation and working with containers in general. This is the Popper, my project is mainly around the Popper container native workflow engine. And I want to start by unpacking what these terms mean, container engine and workflow engine. So container native workflows, and I want to start by covering the basics of containers. What is a container? Container is OS level virtualization that basically you pack an application and all its dependencies, as Tanu was mentioning, without a container image. And a container image is, you can think of it as just a tarball, compressed tarball with all the files and contents of an application. You share that, and the Linux kernel has the capability of isolating applications by making use of Linux kernel features such as file system namespaces, process namespaces, and all these isolation mechanisms and resource constraint mechanisms. And it is often compared against virtualization, in case you are familiar with how virtualization works. In the world of virtualization, we are virtualizing the hardware, so we have a hypervisor on top of the host operating system. And that hypervisor is it's giving the illusion of having a complete hardware machine. And the downside of that is that you have to package with each application the guest operating system. Whereas in the case of containers, you assume Linux, and you only care about the software stack from the operating system up. So containers, what are so popular, or what have been popular with from Docker, with the advent of Docker? So one of the main benefits from the user's point of view is that you basically bring your own environment to share infrastructure. Before this, there was always the case where you would try to run something locally and it would work, and then you try to share that with someone else, and it doesn't work on another people's environment, because as how Tanu was mentioning, you have these environment related things that you're not keeping track of it, and as Tanu pointed, it's depth, right? It's something that you're not documented that has to be documented. And containers allow you to document this, because the way you create a container is you upfront specifically say which software your container is going to contain. And examples, one that I like to use myself is this about a LAMP stack. If you're not familiar with a LAMP stack, it's basically what back in the day you would use to host the web page. You would have Linux and Apache and either MySQL or Postgres, and then you would have to install this, maybe a mailing daemon. You would need to install all of this. It would be time consuming. Nowadays, it's just a command. If you have Docker installed in your machine, you do Docker run, pull that image, and it all works. And in the context of more data science, which is very popular right now, you have like things like TensorFlow that, depending on what you're using, it's not trivial to pack. There are a lot of system libraries that you might be using that you might need to compile and then install, and containers allow you to make that easy to reuse. So this has made, on top of many other things, but this has made containers very popular. And if you kind of fast forward this usefulness and you start seeing people using container more and more, this paradigm of container native arises. And by container native, what we mean is one makes use of containers for basically everything you do in your day-to-day life as a software engineer, as a researcher. Basically use software that runs on containers to build software, to pre-process data, to test programs, to validate results, to visualize results, and all the end-to-end workflow of our activities as researchers or as programmers or engineers. And basically what you can think of is that if that if you want to make use of software, you don't install it anymore. You don't do apt-get or yum install on your machine or homebrew in a Mac. Rather, you pull a container from a registry. And of course, I'm excluding from these personal productivity tools like a text editor, a web browser, although some people are running web browsers in containers, or email readers or calendar applications and whatnot. But if you follow this, then like in my case, my laptop it's very clean. Right? I don't have to worry about anymore about having conflicting versions of multiple, for example, Python versions or multiple compilers and whatnot. I can just install the base system and then do everything in containers. So what that looks like is a container native workflow is that if we abstract a workflow, we have a series of steps, and for each step, it's a particular task that we are carrying out. Then for each of these steps, there is a container associated to it, right? For example, in this particular case, we've been talking about networking simulation experiments. You might be downloading some input data set, and then you have a curl image. And it might seem trivial to download curl, but there's actually issues of reproducibility that arise when you, even just with using curl, right? Because different versions of curl have different features, behave differently, have different flags, different command line arguments. And even something as tiny as curl, running it in a container makes it easier for others to repeat what you've been doing. Then, for example, the experimentation phase, you might be using some simulation, network simulation framework like Contiki. And then for plotting results, some Python-based stack or Jupyter or whatnot, but again, in the form of a container. And this same workflow, you can picture it for basically any other tasks you might, for example, if you're working on a software project, you might be downloading a compiler, then running tests in a particular environment and analyzing results and all the tasks of a software engineer. If we follow this approach and we start to make use of this paradigm or follow this paradigm in what we do, we eventually, of what we've seen in our case, is that there are some things that arise that are of practical nature. Like the first one is that when you use a Docker container engine like Docker or Singularity, initially one starts working with a single container image, but eventually the more complex and the more comprehensive the workflow becomes, then you realize that working with a single image is not practical. So we have this need of interacting with multiple containers and having to define tasks that are separated by multiple containers. So we have these multi-container workflow that we need to express, and that tools don't have support for these out of the box, like Docker or all the other container engines. The other thing is that there are the more these container native paradigms becomes mainstream, there are more and more container engines that keep popping up. Each of them have different purposes, but it's quite overwhelming to start looking at all these options, and it's not only runtimes, but it's engines. And now we start seeing like image builders that are different flavors for building images in a rootless way. And the problem is that interacting with this from the point of view of the user is not the same. The way I work with Singularity, it might not be compatible with Podman or with Pouch or with some of the others that are available. And there's also the issue of if I'm not running on my host machine, but rather I'm running on shared infrastructure, then the manager, the system that manages that infrastructure, has some of them, or most of them nowadays, have support for containers, like in the case of Slurm, Kubernetes, or CI services like Travis and all these services that are available. They have support for containers. The problem is that it's not a common orchestration framework. So the way I work with containers in Slurm is different from the way I work with containers in Kubernetes and so on. The goal of Popper is to try to solve all these, and I'm going to explain how we address these. The first one, the multi-container approach, is it's very simple. The way we deal with it, it's basically having a workflow specification syntax. It's a YAML file that it's a thing wrapper around what you would otherwise be doing manually on a terminal, on a command line. So instead of typing Docker run this image and pass these arguments, we codify that in a file. Say, okay, this step, the first step in our workflow, is making use of this image, and we pass these arguments to this image. And by doing this, we are generating a machine-readable file that can be shared, can be version controlled, and can be consumed by other people, by Popper in other people's machines. And this basically is, or the way we try to think of it, is kind of a very thin augmentation to Bash, to Bash commands. So it's our goal, or one of the principles behind Popper, it's to the very as close as possible to Bash, because Bash is what you interact with on a terminal. If you look at these workload specification, and you specify the logic of your workflow and the containers you're making use of, but you don't have to specify what you're using. In this case, this Docker is referring to a registry rather the underlying engine. So, and this takes us to the next point, which is how do we deal with all these different container runtimes and builders and so on? When we have a workflow, and which is as I mentioned, a series of multiple containers stitched together in a task, in a job. And we have these myriad of container engines. My workflow at the logical level, I really don't care that much on which container engine is the one on the underlying machine that I'm running on. So what Popper works as, it's an abstraction layer between your container runtime, your container engine, and the workflow and the logical pieces, which is what we care about. I care about order. I care about which software I'm using, and what arguments and inputs I'm passing to those images. So, in practical terms, what this means is that when you have that file and you say Popper run this file, this workflow, if you don't specify anything and you're on a Mac or on a Linux machine, then you're gonna assume Docker. But let's say we're running on Singularity, on a host that has Singularity and that it only has available Singularity, then we can just say, okay, I know I'm running on Singularity now. Please make use of that underlying container engine, and everything else, it's exactly the same. So Popper takes care of taking an image that it's on an OCI compliant format, just translating it to the underlying container engine's format that it's more appropriate for it to run, translating those commands to the engine specific commands, but from the point of view of the user, everything is the same. If you look at builders, there are container engines can build commands, but now we have these standalone builders that allow you to build container images as part of in user space. So, for example, if you build a container image on Docker, you need to basically have root privileges. So there's a bunch of new tools that are solving this issue of not needing Docker, not needing root for building images. But again, from the point of view of a workflow, I know that if I'm running, for example, if I have a local Docker file that I'm referencing, all of these tools support Docker file. It's the common denominator. Docker files and OCI formats are the common denominator across all these tools. So what I can do is, again, put an abstraction layer, Popper as an abstraction layer on top of different builders. And if I do Popper run and there's an image that needs to be built as part of the workflow execution, then we build that image on, let's say, Docker. But if I want to use another builder because maybe I cannot run Docker in root mode, then I would say, okay, use BuildKit, which doesn't make use of root. Again, same issue with orchestrators. There is, as I mentioned, a lot of orchestrators that have support, either native support, as in Kubernetes, or add-on support, as in the case of Slurm, and others. But again, from a point of view of the workflow writer, I don't really care that much. And so what I want to say is Popper run, use Docker in my local machine. But let's say I'm on Slurm. Now I want to say, okay, run this on Slurm, and Popper takes care of passing the Slurm specific options to the underlying orchestrator. And the same for other formats that might be external to Popper, but that we want to be able to run. For example, in the case of CI services, we say, okay, I have exactly the same workflow. I want to run it in, let's say, Travis. And Popper takes care of generating configuration files for Travis. So it's kind of like a Swiss knife in the container ecosystem world. And another way of looking at it is that we are escalating this abstraction, these levels of abstraction. So we have containers which are abstracting on top of different operating systems. But then we have all these different options at the container level. So we have Popper as a way of abstracting workflows on top of these container systems. And our goal is to have something like to make it possible for people doing research or software developers that are writing these instructions that are in narrative form, or you can picture this as a README, like in this case, showing a paper on the left that was published at an SC conference. And then you see on the right what it's called as the artifact description, which explains how to reproduce the results containing this paper. So what we want to make available is this option of, in addition to having this description, being able to have something that is machine readable and that people can quickly consume and build on top of. Because the narrative might be incomplete or error prone or outdated, and many of the things that get associated with this type of format. Examples of how we make use this in practice in our lab is, for example, Jaijeet is going to describe later today. He's been working on a very comprehensive end-to-end benchmarking of Ceph and Skyhook DM, which is an extension of Ceph, on Kubernetes. So what these workflows do, for example, is they allocate resources on Cloud Lab, deploy Kubernetes, then deploy Ceph via Rook, run benchmarks, plot results on Jupyter Notebooks. And all these is end-to-end, it's quote unquote Popperized, and is available for others. If you have a Cloud Lab account, you just specify your credentials and everything works out of the box. Complex C++ projects that have like big dependencies in terms of compilers and third-party dependencies, again, can package their dev environment in the form of a container image. And this lowers the entry barrier for new contributors of these type of projects. Machine learning examples, we also have examples later today on how you can install libraries that are not necessarily pure Python libraries, so you need to compile them. You need to install them first at the system level and then install Python wrappers around them. and download data sets and train and evaluate these models and plot results. And other examples that we have on our website that you can have access to. So one of the things that we are discussing later today, is the cross summer internships. And I'm very excited to see all these great students present their results. I'm gonna give a very brief intro to their talks. And you'll find more in the lightning talks and later in the poster sessions. We have Jajit, as I mentioned. He worked on workflows for automating Skyhook DM, which is a Ceph extension from Ceph on Kubernetes, as I explained. Nicole Castillo, she worked on implementing workflows for carrying out performance comparisons of machine learning libraries. This is also very exciting, very data sciencey, very in these days. Fernanda Dominguez, she worked on workflows for representing SPDK performance comparisons, particularly taking SPDK, compiling SPDK, and also conditioning storage devices so that you can actually make sure that your results are coming from steady state scenarios rather than unstable underlying storage behavior. We have Eddie that he worked on adding support for Postman to Popper, really exciting as well. And last but not least, Anders Borrell, he has worked on creating guides on how to follow this computer native approach for computational science for both Python and R. So if you work with notebooks and you are like a notebook heavy user, then how can you embrace these paradigms, and can you find a guide? And Anders has been working on this. The next steps, we're focusing heavily now on community management. In particular, we're joining a community of community managers that is led by John O'Bacon, which is a famous community management theorist, I would say, in the open source world. We're taking part of that. We're excited to see what comes out of it in terms of how we can make Popper a nicer community for contributors. And then what I wanted to get your feedback on is this idea of the Popper cloud. The idea is that, as I described, you might be working on locally on your machine, you following this container native approach. All might be going well, you're using Docker or Podman, but then eventually there's some sort of resource allocation problem. You might not have enough memory, you might not have GPUs, you might not have certain type of storage devices or whatnot. And at that point, since we have support for running in Kubernetes, we could have a service that it's kind of like always running, waiting for requests. And we have a way of logging in. If you have an administrator that set that up, maybe it has like even like single sign-on, where you can say, okay, I want to log in to this Kubernetes instance, and you very quickly you register or log in and get access to a config file, a YAML file that you can pass Popper to, and then so when you're running locally, you can quickly say, okay, this is like, for some reason I cannot, or this is taking just too long because I don't have enough resources, but I already debug it and I want to scale it up. I can now say, okay, running Kubernetes using these credentials that I got from my sysadmin or the automated login process, and this would automatically transfer to the cloud. This is an idea we're floating around, starting to socialize, create an open source framework around it, and I'm curious to see your thoughts on this. As I mentioned, we have the upcoming lightning talks. Looking forward to those, and I think that's pretty much it.
So Ivo, if I could make a comment.
Sure.
Yeah, so I like the Popper Cloud idea because I mean, I find that one of the things that is kind of a big barrier to people when they kind of is this kind of phase transition to working locally to working, you know, on a set of, you know, cloud resources or whatever, right? And so, yeah, I think the idea of a you know, some kind of service and framework that makes it relatively easy to move what you've been doing locally, kind of without having to spend a lot of time learning about like the cloud that you're using or whatever. Sounds like a really, really great idea.
Awesome, thanks. By the way, that's Rob Ricci from Cloud Lab in Utah.
Okay.
Thanks, Rob.
Sure.
So Ivo, my question was that, like, let's say if we have something like a SI unit and want to use Popper for multiple SI units, so in some senses it's not a Docker container, then but has, you know, the description of all the data content, or in some senses the code, how would we use Popper in that sense?
You mean like you don't have the workflow? You would like to construct the workflow, or?
Here it seems the adoption of containers seems the requirement, right?
Yes.
If it's a package like a SI unit, which is not necessarily, but it has, let's say, descriptions of what it contains internal to it.
So the common denominator in all these ecosystem is Docker files and OCI formats, or an engine that can understand Docker files. If you're working locally, then you can say, okay, I have these Docker file, has instructions on how to install things in a container image, then create that environment. It doesn't have to be a container engine, although that's what Docker files are used for, but you could have a no engine that, given a Docker file, just installs everything on your host. I don't know if that would be useful, but that just for the sake of—
yeah, that kind of answers it, in the sense that if we have multiple SI units, if we can create our Docker files through, you know, what we are doing through depgen, then looks like—
if you can generate the Docker file automatically,
yeah, that's
then
what
generate the
sorry.
I was just gonna say, generate the commands that would prepare the system for me. And if you have that, then from that to Docker files, it's a quick tiny step.
Okay.
Any other question before we wrap up for break? Quick lunch break.
So how do we get to the poster now with this? So it will be over here itself?
It's this session, yes. I believe we're gonna leave it running.
Oh, sorry, for the poster sessions? Okay, that segues to me. I'm probably gonna, the poster session, the lightning talk started at 1, and I will likely close off this session once we're done here and turn off for lunch, but then open back up a little bit before 1 o'clock for people to join again. The lightning sessions will start, which is, they're all pre-recorded, and the students should be in the participating on the Zoom call at the same time. Once the recording, once the lightning talks are done, the students will then go to different separate Zoom rooms. So not this one, they'll go to a separate one that they've set up that they're hosting. And that link is I'll put the link in the chat when we get back, but I also just put it, pinned it in the Slack on kind of the general channel, as well as the reproducibility channel. And it's also on the main agenda. So the link to the list of Zoom rooms are on the if you go to the lightning talk and select that link, you'll go straight to the document with each individual student's Zoom room. So there's definitely a few places you can find it. If once we're done with the actual lightning talks at about 1:30, I will make sure I post it again so it's visible to everyone on this Zoom room. So you can always find it by coming back here and clicking on the link that would be in the chat. And I'll be on at that point, so I can also help you out. Okay, is that clear? Real good. Okay. All right. All right, great. If there were no other questions, then I'm going to wrap up this morning session. I will be stopping recording now and also stopping this session.